All right. Hello, everybody. Hope you're doing well. Sorry I'm a couple minutes late. I was juicing some limes because I'm making some carne asada and it's part of the marinade, and it just takes me a long time to juice limes for whatever reason. So, um, there's going to be no Discord today because I'm having a chat with the science department after this, and it looks like the results of the straw poll are in, and we will be studying special relativity. So that should be interesting. There's a lot of math I can teach you for special relativity. And then if we have extra time, I will go into one-dimensional quantum mechanics because that was the second most voted topic. All right, so let's dive right into it. So we're doing the 2010 free response today for mechanics. Looks like this is going to be one about air resistance. It says students are to conduct an experiment to investigate the relationship between terminal speed of a stack of falling paper coffee filters and its mass. Their procedure involves stacking a number of coffee filters, like the one shown in the figure above, and dropping the stack from rest. The students change the number of filters in the stack to vary the m while keeping the shape of the stack the same. As a stack of coffee filters falls, there is an air resistance or drag force which acts on the filters. The students suspect the drag force is proportional to the square of the speed, so the drag force is cv squared, where c is a constant. Using this relationship, derive an expression relating the terminal speed v sub t to the mass m. So at terminal speed, at v sub t, we're going to have the drag force is balanced by the weight force. Okay? Because those two forces are going to be equal and opposite. So that means that cv squared has to equal mg. All right? Which means that the terminal speed is going to be square root of mg over c. So we're going to have a square root dependence on mass. The students conduct the experiment and obtain the following data: mass, terminal speed. Assuming the functional relationship for drag force above, use a grid below to plot a linear graph as a function of m to verify the relationship. Use the empty boxes in the data table as appropriate to record any calculated values you are graphing. Okay, so you can see that I'm putting mass on the horizontal axis. So if I want a straight line, if I go to this relationship right here, I get v squared equals g over c times m. So if I have m on the horizontal axis, and if I put v squared on the vertical axis, then I get a linear relationship with slope g over c. Okay? So what I want to do is I want to put v squared on the horizontal, or on the vertical axis. So this should be v sub t squared. So let me type that in. I'm going to square the terminal speeds here. Okay, so 0.51 squared is 0.26. 0.62 squared is 0.38. 0.82 squared is 0.67. 0.92 squared is 0.85. And 1.06 squared is 1.12. All right. So these are our data points. And I can see that I basically need my graph to go up to 1.2. So if I make this 1.2, 1.4, if I make this 0.2, oops, okay, so 0.2 is going to be right there. All right, and then here, I'm going to do this in times 10 to the minus 3 kilograms. And then it looks like this would be, we can see the largest mass is 5 times 10 to the minus 3, so maybe I make, move this, that's 1 times 10 to the minus 3 kilograms. Okay, so now I can plot my points. My first point is 1.12 and 0.26. So 1.1 and 0.26 is roughly right here. My second data point is 2, 0.04 and 0.38. So a little bit more than 2 and 0.38 is kind of like maybe right here. Then I have 2.96 and 0.67. 2.96, 0.67 is roughly right here. 4.2 and 0.85. 2 and 0.85. That's maybe right here. And then 5.1 and 1.12. About right there. Okay, so we make our line of best fit, like so, and it looks pretty linear. That's pretty good. Let's shift that down, like so. Cool. Use your graph to calculate C. So I can see that my slope, based on this, so I did part B. Part C, I can see that my slope is, it has a rise of 1.2 meters squared per second squared. And it has a run of roughly 5 point, I'm going to say 5.7 times 10 to the minus 3 kilograms. So if I do 1.2 over 5.7 times 10 to the minus 3, I get about 210.5 meters squared over second squared kilograms. All right. Hey Mo, hey Zach, hey Alex. So then I set that equal to gravity, which is 9.8, over C. So I can solve for C. So that tells me that C equals 9.8 divided by answer 0.046. Actually, more like 0.047. And the units on that, it looks like, are kilograms per meter. All right. So, C, oh, that was I. We just did I there. So part C says a particular stack of filters with mass m is dropped from rest and reaches a speed very close to terminal speed by the time it has fallen a vertical distance y. Sketch an appropriate graph of speed versus time from the time the filters are released up to the time t equals capital T that the filters have fallen a distance y. Okay, so I'm just going to make the terminal speed is like right here. Okay, and so basically what this graph is going to look like is something like this. It's going to asymptotically approach the maybe something like that. So the initial slope is going to be 9.8. So this slope at time equals 0 is 9.8. Maybe t equals capital T is roughly right here. So it's almost reached its terminal speed. All right, so I did part I. Now let's see part II. Suppose you had a graph like the one sketched in CI that had a numerical scale on each axis. Describe how you could use the graph to determine the distance y. Basically, I would set the area under the curve equal to y. Okay, so I would say, gee, this area, oops, I would say, gee, this area up to this point, all that area, that's equal to y. All right, so now moving on to part D, determine an expression for the appropriate amount of mechanical energy dissipated, delta E, due to air resistance during the time the stack falls a distance y. Express your answers in terms of ym, v sub t, and fundamental constants. Okay, so if we think about it, the initial energy equals the final energy plus the energy that was dissipated. So the final energy is going to be less than the initial energy. Okay. And the reason for that is because some of that mechanical energy was dissipated as heat. So the initial energy is gravitational potential energy, mgy. The final energy is kinetic energy, but the kinetic energy is not the actual amount of kinetic energy that it should have, because our speed is capped off at the terminal speed. Okay? So normally this would be a larger velocity, but it's not going to be as large because our speed is capped at terminal speed, so the kinetic energy is capped at a maximum value. So we can rearrange this expression. We get that the energy dissipated is, so I'm just subtracting this from both sides, mgy minus 1/2 mv sub t squared. Okay? So it looks like that's it. Nice. Question 2. A bowling ball of mass 6 kilograms is released from rest from the top of a slanted roof that is 4 meters long and angled at 30 degrees, as shown above. The ball rolls along the roof without slipping, so it's rolling. It's rolling, everybody. The rotational energy of the sphere of mass m and radius r about its center of mass is 2/5 mr squared. On the diagram below, draw and label the forces acting on the ball at their points of application along the roof. So we're going to have some sort of a frictional force which acts tangentially to the ball. Okay, so it acts right at the point of contact with the surface. We have a normal force, which again, normal force is going to act perpendicular to the surface, and it's going to act from the point of contact. Okay, I'm not labeling these because it takes too much time to do that. Hey, James. And then the weight force acts through the center of mass. Like that. Okay? So I think those are the only forces. Calculate the force due to friction acting on the ball as it rolls along the roof. You do not need to draw anything other than what you have shown in Part A to assist in your solution. Use the space below. Do not add anything to your figure in Part A. All right, so I did Part A. So now for Part B, I can see that friction, normal force, so the formula for torque is F perp times R. All right, and I can see that the normal force is not perpendicular, it's actually parallel to R because it acts through the center. So normal force is not going to exert any torque. The weight force has R equals 0 because it acts through the center of mass. So the only force that has a non-zero torque is friction. Friction is, I'm going to go ahead and call down the incline as positive. So friction is going to exert a positive torque of F times R. Okay, so that's the net torque, and that's equal to I alpha. So that's Newton's second law for rotations. Then I also have a linear form of Newton's second law, which says that, so in the y direction I have mg sine theta, pulling the block down the incline. I have friction opposing it, and that equals ma. So this is the rotational form of Newton's second law. This is the linear form of Newton's second law. And then I also have geometry, which says that A equals alpha R. So that relates the rolling with the translating. Okay? So I'm trying to solve for F. trying to solve for F, so I can, what I'm going to do is I'm going to go ahead and substitute A in right here. All right, so I can cancel out a factor of R there, and then you can see I have R alpha, so I get friction equals 2/5 MA. All right, so that's this equation, and then I can see that MA is equal to mg sine theta minus friction. So adding the friction term over to the other side, that says that 7/5 friction equals mg sine theta, or equals 2/5 mg sine theta. Okay, the 5's cancel out, and I get that friction equals 2/7 mg sine theta. Okay, so that's we learned that technique for the system of equations for objects that are rolling. We do a Newton's second law for rotation, you do a linear Newton's second law, and then you do geometry for each object. Let's see if I have any questions. All right, part C says calculate the linear speed of the center of mass of the ball when it reaches the bottom edge of the roof. All right. So I'm going to go ahead and plug this into that equation right there. So I have mg sine theta minus 2/7 mg sine theta equals ma. So I can see that the mass cancels out, and I get that the linear acceleration is equal to 5/7 g sine theta. All right. So then it's a matter of kinematics. So I have v final squared equals v initial squared plus 2a delta x. So it says the roof is 4 meters long. It starts from rest. I think it says it starts from rest. Yeah. So that's 0. So I get v final equals square root of 2a delta x. So the delta x is 4. And then the a value would come from this. So 5/7 times 10 times sine of 30 degrees, which is 1/2. So I get 50 over 14 as the acceleration. 3.57. So I get 5.3 meters per second is the speed. All right. Boom. Part D says a wagon containing a box is at rest on the ground below the roof so that the ball falls a vertical distance of 3 meters and lands and sticks in the center of the box. The total mass of the wagon and the box is 12 kilograms. Calculate the horizontal speed of the wagon immediately after the box lands in it. Okay, so this is kind of weird. It sort of suggests that you should do projectile motion, but really projectile motion doesn't matter. So if we look at the speed of the box, or the speed of the ball, I should say. all right, this angle is 30 degrees. And the speed is 5.3 meters per second. So the horizontal speed of the bowling ball is going to be 5.3 cosine of 30. That's 4.63. Okay? So the initial x momentum of the system is going to be m times v sub x initial. And when I say initial, I mean at the moment that the bowling ball leaves the surface, or leaves the hill. So that would be 6 times that, because the mass of the bowling ball is 6, which is 27.7. Actually, more like 27.8. Now, the initial x momentum has to equal the final x momentum. Okay? And it says that now, y momentum is not conserved because we have gravity acting vertically. We have normal force acting vertically when the ball hits the ground. So those external forces are going to change the y momentum. But the x momentum is, in fact, conserved. So what's the final mass of the system? Once these two things stick together, we've got a bowling ball of mass 6 kilograms and then a wagon, which is 12 kilograms. So that gives 18 kilograms is the final mass. And so we can use that to figure out the final velocity. And it's roughly 1.54 meters per second. Okay? So that's kind of weird, because see how it tells you how far the wagon is going to fall. So it kind of suggests that you're doing some kind of a, maybe a projectile motion problem, but really that's totally unnecessary. Okay, number 3. A skier of mass m will be pulled up a hill by a rope as shown above. The magnitude of the acceleration of the skier as a function of time can be modeled by the equation blah. Where there's some constants. The hill is inclined at an angle of theta above the horizontal, and friction between the skis and the snow is negligible. Derive an expression for the velocity of the skier as a function of time during the acceleration. Assume the skier starts from rest. So the velocity is the integral of the acceleration. Okay, so the velocity as a function of time is the integral of the acceleration from 0 to time t. So we're integrating a max sine of pi little t over big T dt. And so doing that integral is going to give us negative big T over pi, a max, cosine of pi, little t over big T. And I will not forget my limits of integration like I did yesterday. And so that gives us minus big T over pi, a max, times the quantity cosine of pi t over big T minus 1. So I get a max big T over pi times 1 minus cosine of pi t over big T. Um, all right. So, but this equation is only valid, so we can see that the speed builds up, and then once we get, so this is for 0 less than little t less than big T, so t between 0 and big T. But once we reach big T, the velocity maxes out, okay? So I should just plug in little t equals big T to get the peak speed, because notice how the acceleration goes to 0. So we just achieve that speed and then we keep that speed. And so if I plug in little t equal to big T, this term becomes cosine of pi, which is 0, and we get a max speed of at over pi. So it's a piecewise expression. Derive an expression for the work done by the net force on the skier from rest until the terminal speed is reached. All right, so work. Okay, so first of all, the net force is going to be ma. So it's going to be ma max sine of pi little t over big T. Actually, you know what? I know a better way to do this. We're going to use the work kinetic energy theorem, which says the work done by the net force is equal to the change in kinetic energy of the object. The initial kinetic energy of the object is 0, so the net work is just going to be the final kinetic energy, which would be 1/2 m times the final velocity squared. That's the work done by the net force. Okay. Part C, determine the magnitude of the force exerted by the rope on the skier at terminal speed. So we've got the component of the weight force that's going down the incline is mg sine theta, and the rope is what is pulling it up the incline. So if we're at our terminal speed and the acceleration is 0, those two had better match each other. I don't see friction is playing a role. Yeah, so that's a pretty simple part. Derive an expression for the total impulse imparted to the skier during the acceleration. So impulse equals change in momentum. So the initial momentum is 0, so the impulse is just going to be the final momentum, which would be ma max t over pi. So that would be the impulse. Suppose that the magnitude of the acceleration is in. So this question is kind of just about like definitions. It's really quite simple. Suppose the magnitude of the acceleration is instead modeled as exponential decay. On the axes below, sketch the graphs of the force exerted by the rope for the two models from t equals 0 to time t equals big T. To a time little t greater than big T. Label the original model F1 and the new model F2. So if we look at the first model, the acceleration is sinusoidal, And at little t equals big T, the acceleration is equal to a max. Okay? So, so we're going to have some kind of a sinusoidal dependence. So something like let me see here. Oh, I have to be a little bit careful here because it wants the force exerted by the rope on the skier for the two models. So if I look at F1, let me make sure you guys can see this. If I look at F1, I know that the force exerted by the rope is going to be, so the tension in the rope is going to be the net force plus mg sine theta. Okay? Because the net force is going to be tension minus mg sine theta. So, and then the net force is just ma. So, what we would get is m a max sine pi t over big T plus mg sine theta. All right, so this is F1. So if I graph that function, we can see that at time equals 0, it's equal to mg sine theta. And then it grows sinusoidally like this. And then after time big T, it immediately drops to 0, like that. So this is going to be F1 because we have an abrupt change in the acceleration. For F2, we're going to have, again, ma plus mg sine theta, so we have m times a max e to the minus pi t over 2 big T plus mg sine theta. So this one is going to have some kind of an exponential decay like this. Like that. Okay? So that's what those graphs are going to look like. Hopefully that's, okay, that's it. Wonderful. All right, class, that's my lesson for today. I hope you found that useful and enjoyed learning about the wonders of mechanics. All right, I will talk to you tomorrow. And, oh, by the way, it looks like the results of the straw poll are special relativity. I can't remember if I said that already, but we'll probably do special relativity first. And then the second place was one-dimensional quantum mechanics, so we'll move on to that afterwards. All right. Have a great afternoon.